Newton's law says that there is a gravitational attraction between any objects that have mass. But gravity isn't the same everywhere. In fact, it varies ever so slightly across the globe due to both geologic features below the surface and elevation. One way to find subsurface features or objects is to measure the gravitational attraction that the Earth exerts at locations near buried features. But first, let's define gravity. Gravitational attraction can be expressed as an acceleration. When an apple falls from a tree, it accelerates downward. Scientists call this gravitational acceleration small g. After the apple lands, gravitational attraction holds it to the surface. Newton's law of gravitational attraction defines gravitational acceleration, small g, of one object due to another mass. Let's read this equation. Big G is a universal constant that is the same everywhere. M is the mass producing the gravitational attraction. R is the distance between that mass and the object experiencing the acceleration small g. This equation gives us two reasons why small g varies ever so slightly from place to place on the surface of the Earth. First, the law says that a greater mass m will cause greater gravitational acceleration, that is, greater g. Second, the law says that small g also depends on r, which is the distance from the mass m. Because r appears in the denominator, a larger r, meaning a greater distance, causes a smaller gravitational acceleration, g. What does this mean for measuring gravity on Earth? Differences in the gravitational acceleration from one location to the next are tiny, so we don't feel them as we move around on the surface of the Earth. We use a large spring here to exaggerate the differences. A longer spring equals greater g. Looking below the surface, we see that the denser or larger an extra mass below the surface is, the greater the local g will be. It also means that g will be greatest closest to or right over a denser mass like an ore body. An ore body is a zone of rock that contains a high concentration of minerals that would be worth mining. Further away from the ore body, g decreases. These two aspects of Newton's law explain why, if we wander the Earth with sensitive instruments measuring g, we'll see differences due to extra buried mass, like that ore body, or missing mass, like a tunnel. Missing mass in the Earth reduces the g nearby. Thus, it reduces the stretch in the spring. Again, where the gravitational acceleration g is greater, it causes extra stretch in the spring. A gravimeter, or gravimeter, is an instrument that contains a highly sensitive spring. If you place it on the ground and let the spring settle, it can detect differences in gravitational acceleration smaller than 1 part in a million. That can be plotted on a graph. As you move the gravimeter from place to place, it senses these tiny differences in gravitational acceleration. The graph indicates where there is lower than expected gravity, shown as data points below the dashed zero line, and higher than expected data points above the line. In this example, the graph shows the low g above the tunnel and high g above the ore body, as would be expected. Soils, rock layers, and aquifers also affect gravity readings because of their different densities. Remember when we said that gravity depends on elevation? In fact, the farther you are away from the center of the Earth, the lower the gravitational attraction. Using a highly sensitive gravimeter, you can measure the decrease in gravitational acceleration as you go higher in a building. Because of this known elevation effect, the height of the ground with respect to sea level is always measured, often using GPS, and recorded. It's necessary to correct for the effect of elevation on readings to detect subsurface features. In fact, the gravity differences due to buried masses are so small that scientists need to correct for not only elevation, but other effects that influence the gravity readings. One of these other effects is called instrument drift. Even if the gravimeter is kept at a fixed location, the readings will gradually change or drift over time due to gradual changes in the behavior of the spring itself and other factors. A critical correction called the drift correction needs to be done to the raw instrument readings. A drift correction requires that the user records the time of each gravity measurement along with the elevation. More details about how to use the elevation and time measurements to correct the raw gravity readings for elevation instrument drift, and other factors are described in a separate animation.